Hello everyone, and welcome to this quick introduction video for physical chemistry, quantum mechanics. Today we are going to be going over a quick overview of classical mechanics versus quantum mechanics. My name is Becker, and let's get started. Simply put, the laws of classical mechanics govern the macroscopic of our world. This could be anything like a baseball, people, or even skyscrapers. It's things we can see and physically interact with. Of course, plenty of laws and equations make up classical mechanics, and those include Newton's laws, such as his first law, the law of inertia, second law relating force, mass, and acceleration by F equals ma, and his third law, for every action there is an equal and opposite reaction. On the other hand, the laws of quantum mechanics govern the microscopic. This is going to be things on the atomic scale and include electrons, protons, and even light particles. So with a basic understanding of classical versus quantum mechanics, let's get into some examples. So consider this. If you push a ball with a certain velocity toward a bump, how do you know if this ball will cross this hill? Well, we can calculate the kinetic energy of the ball just using the simple Ke equals 1/2 mv squared, and then compare that to the potential energy requirement to actually go up the hill. Potential energy, or gravitational potential energy, equals mass times gravity times the height. So if the kinetic energy of the ball is going to be greater than the potential energy required to climb the hill, then the ball will cross this. And this happens every time. That is an important feature of classical mechanics. We can predict with 100% accuracy whether the ball will cross the hill or it will not based on its initial energy and the energy threshold. But what if we push an electron at this hill? Will it cross consistently every time? Well, classical mechanics says yes, but experiments show a variation in whether it crosses or not. You see, if we took 100 identical systems and gave this electron a certain force, it would cross our hill in some of the cases and not cross it in the others. We can kind of see that right here. Now, if we replicate this scenario enough times, we will be able to obtain the average probability that our electron can cross this hill, but we will not be able to predict with 100% accuracy whether it will cross or it will not. So as we can see, the rules and understandings of classical mechanics are not enough to understand how particles work on the quantum level. Therefore, we must develop new rules to accurately model what is going on. There are plenty of experiments showing just how these particles work, whether they act as a particle or wave, something we'll get into later. Some of those experiments include the double slit experiment, showing off the wave nature of particles, the photoelectric effect, showing off the particle nature of particles, blackbody radiation, showing off how a substance emits a particular frequency of light based on its temperature, and so on and so forth. For now, we will cover this at a later point. Anyways, thank you all so much for watching, and I hope you have a great day.